Hey guys, today I wanted to make an update video on Lil Sgt Chonky. So in order to increase reliability, I've replaced the wooden plate with the aluminum version. This tram plate for the spindle was a printed part, so I have replaced that with the aluminum version. And this inversion plate I designed and made a few days ago out of aluminium. So if you remember, I have this box, and I have a limited height in Z, which means that in the default setup, if you put the motor on top, it doesn't fit into the box. So that's why I have a belt here, which puts the motor behind the spindle, and yeah. So this plate has the motor mounted in slots, so this entire assembly can slide back, and we have a tension screw here. And because I'm super lazy and the only tool I have is a CNC, and I don't like changing tools or flipping anything, I design things mostly so I can mill them in one setup. So just cut from the top, and I'm gonna take this apart, and then I'm gonna show you how I managed to get the screws in at 90 degrees. I think that's quite cool. So see you in a bit. So I'm first gonna show you the first version of basically this here. So this is a printed inversion plate, and this is my old Z plate. And so imagine you have the ball screw mounted here. The ball screw, the bearing block is mounted at the top. Then you have this inversion plate, and then you have a bunch of screws that go through this plastic piece, through the bearing block into the wooden plate. And this never was very stable, mainly because this is wood. This is printed, it's cantilevered. On top of that, I designed this so the tensioning would not be a linear sliding motion. It was actually designed so it rotates around one screw. However, the problem was that these slots that were angled, so the motor could actually rotate around the screw. The motor didn't really slide properly, so this tension block here that was pushing on one of the mounting screw also didn't really tension it. And yeah, on top of that, you can just see how much these washers are deformed. Like, the motor was always getting loose, and it got loose more often, and it got worse, so I decided to replace this with aluminum version. And also it was quite difficult to tension these screws in general, because unlike a NEMA 17, the NEMA 23, they, at least the ones I have, they don't have a thread in the faceplate, which means you have a screw, and then behind the faceplate you have to hold a washer and a nut. And in this case I added these pieces or support pieces on the side to prevent this from flexing or make it less flexible. And it was really difficult to get a wrench in here, so I never was able to properly tension the nuts, which just made it worse. And yeah. So I've learned from this part and have moved on to this design. The nice thing about this design is that everything is made out of plates. So everything is made by cutting from the top. So we have a sliding motion. We have a sliding motion, yeah. We do have a sliding motion and it slides quite nicely. At the back here we have a tension screw, and I'm just going to take this apart. So at the top we have 4 screws, and I milled a plate that goes around the motor and adds 4 threaded holes, so I don't have to get a wrench in, and I can basically access all these screws from the top. So the screws to hold down the motor are easily accessible from the top. The screw to tension the belt is also easily accessible. Especially in a tight box, it's really important that like things like these are accessible. Otherwise, if they're not accessible, you have to take the entire thing apart. Like you have to take the machine out of the box, and you have to disconnect all the cables, and yeah. Let's see. So, okay. So, I basically made a plate with holes. Then you slide this plate over the motor, which adds you threaded holes. Then this is a thing I really like to do, because I need a screw or a threaded hole at a 90-degree angle, and I don't want to, you know, I don't have a drill press, I don't have a machine vise. So what I do is, if I need a hole or a threaded hole at a 90-degree angle, I cut a slot, I mill these tiny parts, and it just has these hooks. You basically stick it through, and then you have a hole at a 90-degree angle. I mean, it's not the highest precision, but it works. So this entire thing has been essentially designed along this idea. So all these screws are the same thing. Come on. So we have these slots, then we have these pieces that slot in, and then I made it so that the distance between this part and the edge is 3 millimeter. So then I have this the spacer piece, and then I just take my screw, and of course it's a bit difficult on the video while I'm talking, but that's how I get screws at a 90-degree angle, by just using plates. Yeah, I just basically wanted to show this idea because I think it's cool. If the only thing you have is CNC, is you have to get creative. I mean, the professionals, they will probably think like, oh, you made a single part into 1, 2, 3, 4, 5, 6, 7, 8 parts. And yeah, it's 8 parts, but I was able to make it with my tools, and I'm happy. Otherwise, if I would have to drill these holes with, like, I don't know, I don't even know how I would have made this. The precision would have suffered a lot. So yeah, I just showed on the wooden plate. Yeah. If the holes were there for this piece, it would just screw in at the back and a line at the top. Here's another thing I also learned. I made, this was the first aluminium version. And what I tried to do is, I milled a slot into the side. However, the slot was a little bit too narrow, and so it actually didn't go in properly. So on the next version, I learned that it's easier or better to just use one edge for alignment, and then the tolerance is not so important. And yeah, I hope you enjoyed this. Hope it was interesting and gave you, like, I don't know, new ideas of how to approach like a problem and solve it with like the tools you have on hand. So see you soon. Bye bye.